Hi everyone. So we're going to go back and look at all the different types of reactions that we have in organic chemistry. So there's 8 main types, and addition is the first main type that we have. So we saw that in addition reactions, we're always dealing with unsaturated hydrocarbons. So these unsaturated hydrocarbons have to have at least one that's a double, or we can have a triple bond as well, where we're going to add something across that double bond, and that double or triple bond is going to break. So in hydrogenation, this is when we're adding hydrogen across that double bond. So we see that in propene, our double bond breaks, and we end up making propane when we add the two hydrogens across it. This requires a catalyst and heat to happen. Halogenation reactions are the same type of thing, but this time we're adding a halogen like Br2 or Cl2 or F2, again, across our double bond. So here, ethene, the double bond breaks, and we add the two bromines, and we have 1,2-dibromoethane. If we have ethyne and limited chlorine being added, we're going to make a double bond. But if we have lots of chlorine, then this double bond is further going to break, and we're going to make a single bond. All right, in hydrohalogenation, we are adding a hydrogen and a halogen across our double bond. So we're going to break our double bond like we have in propene, and we're going to make that into a single bond with the HBr being added across it. Now, this is when we start using Markovnikov's rule, because once we have an asymmetrical compound where the double bond is being broken, we can add HBr or BRH, right? So it depends. So we have to look at which carbon had more hydrogens because the rich get richer. So this first carbon here had 2 hydrogens, so it is more likely to obtain the hydrogen, which is why this is the major compound. Okay, so now we have hydration. So this is when water is being added across. It's easier if we think of water as being HOH, because then we can see that we have the 2 separate groups that are being added. So again, we can break the double bond and add HOH or OHH. And that depends again on Markovnikov's rule. Our first carbon here has the 2 hydrogens, so it is more likely to obtain the hydrogen. Again, why this is the major product, but the other product also gets made. We have to say major and minor. We have to list them both every time unless we're only asked for the major product, but we should be listing them both. All right, so in a substitution reaction, now we're subbing something in and subbing something out. So we can sub in across a double bond or across a single bond. It depends. So if we have an aromatic substitution, we have benzene and it's got their double bonds that are going round and round. So now we can sub one of these hydrogens out. So remember that these are all hydrogen atoms, right, across the benzene. So one of them gets subbed out and the bromine gets subbed in. Or if we have an alkane substitution, we're going to just sub out one of the hydrogens, and then HBr is going to be our other product here. Okay, so now we're into the new reaction. So hydrolysis is the first new reaction that we're looking at. So in hydrolysis, we're adding water to split up a large molecule. So we're going to either add water to an ester. So if this happens, then we get back our carboxylic acid and our alcohol. Or if we add water to an amide, then we get our carboxylic acid and our amine. Or lastly, if we add water to our ether, we get an alcohol and another alcohol. So for example, ethoxyethane can be broken down with water into ethanol and another ethanol. So really we just get one product here because we had a symmetrical molecule. In condensation reactions, we are now going to condense 2 smaller reactants and make a bigger product. So that means that water is removed. So we always have water as one of our products in a condensation, and then we have our larger compound. So we just have to look and see where the water was taken out. So if we have methanoic acid and methanol, here's the OH for the water, and here's the H. So we end up with methanoate. If we have ethanol and methanol coming together, we end up with methoxyethane. So again, we're just going to take out an OH and an H, making the H2O. And methanol with methanamine makes N-methyl methanamide. So just be careful of where everything comes out here. So here's the OH, and then one of these hydrogens comes out that's beside the nitrogen there to make the H2O. Combustion reactions you're already familiar with from grade 11. Nothing has changed here, but even in grade 11, we were looking at them being hydrocarbons that are burning by reacting with oxygen. And indeed, that's what we're looking at. So we can either burn just an alkane like propane, or we can burn something like an alcohol. If we have complete combustion, we only get carbon dioxide and water. And if we have incomplete combustion, we get carbon dioxide, water, carbon, and carbon monoxide as well. This is just balancing, like regular balancing in grade 11, where we're trying to figure out how many moles there are of each of our reactants and products for this to make sense. Okay, type 6 and 7 are oxidation and reduction. So right now we're just going to simplify things by having oxidation being with an oxidizing agent that we're just going to have as an O in either square or round brackets. And we don't exactly know what our other products are going to be, again, because we're simplifying things in this unit, but we know that if we have a primary alcohol that's being oxidized, this will make an aldehyde. So here, this is going to make more bonds to oxygen. That's what we're going to say oxidation is. So here we're going to get one more bond to oxygen, which is how we get our aldehyde. Okay, so an aldehyde can be further oxidized to a carboxylic acid. So if we get more bonds to oxygen, that can only happen here. That hydrogen is removed and we get an OH group instead. Okay, so we're sort of memorizing that when we see a primary alcohol that's oxidized, we make an aldehyde. When we have an aldehyde that's oxidized, we make a carboxylic acid. If we have a secondary alcohol and we oxidize it, if we make more bonds to oxygen, this will make a ketone. Of course, this hydrogen has to get removed when that occurs. So propan-2-ol will make propanone. If we take a ketone and try to oxidize it, we will have no reaction because there's already a double bond here and there's no other place for there to be more bonds to oxygen possible here. So there's no reaction. There's also no reaction if we take a tertiary alcohol and try to oxidize that, because it's not possible to make another bond to the oxygen here because this carbon already has 4 bonds and it can't have 5. So that's not possible either. So some of these cannot be oxidized. And that's one way that we would use if we were trying to differentiate between them, if we had to differentiate between a primary alcohol and a secondary alcohol and a tertiary alcohol. Well, the first thing we could do is try to oxidize all 3. The tertiary would not oxidize at all. So we would know that that's a tertiary right away. Then we could try to look at the difference in the reaction between the primary and the secondary alcohol. The primary alcohol would be a much longer reaction because first it would change into an aldehyde, and this aldehyde would continue on and change into a carboxylic acid. And then we can measure the pH of that. Of course, it would be acidic. Whereas the secondary alcohol would be a much quicker reaction because it's only one step. It would convert into a ketone, which would not be an acidic pH. And our final type is going to be an elimination reaction. So with elimination reaction, we're eliminating. So we're really going backwards of putting something in. Now we're taking something out. So we just have to look and see what we have to begin with. So with the propan-2-ol, if we eliminate water out of here, we have H and OH, we're going to create a double bond. And we make propene. Because this is symmetrical, we end up with just having one possible product, because if we put the double bond on either side, it's still going to create, no matter what, it'll create propene. There's no other choice here. But it is possible to have more than one product when you have something that's not symmetrical and you're taking out a water. So if you take out OH from butan-2-ol, now where does the H come out of? The H can come out of either carbon that's beside this carbon that contains the OH. So it could come out of this carbon, or this carbon on. So the carbon on the right or the carbon on the left. The carbon on the left has 2 hydrogens. The carbon on the right has 3 hydrogens. So this is the opposite of Markovnikov's rule. So the rich get richer, but the poor get poorer. So the carbon with less hydrogens is more likely to lose the hydrogen, which is why our major product is but2-ene. And our minor product is but1-ene. So both are formed, and again, we have to draw both plus water, of course, because we are eliminating the water, but both our major and our minor are formed. So this is a summary map, and you have a summary map that you have available to print and write out as well. So you should be writing out all the different types of reactions that occur to convert one type of functional group to another. But remember that when you're dealing with these, not only do you have to deal with the main type of name, but you also have to remember the subclasses. So if you write that something is addition, well, what type of addition? Okay, is it hydrogenation, halogenation, hydrohalogenation, hydration? Those are all addition reactions. So always write the main type and then the subtypes. Same with substitution. Is it an alkane substitution, aromatic substitution? Sometimes it gets confusing because these go by so many different types of names. We just have to keep all of this information straight. And again, for now, we're really mainly memorizing when we see something what it's going to make. In future years in organic chemistry, we'll study how it is that these are being made when we look at mechanisms for how this occurs. And then it'll make a lot more sense why this is occurring the way that it is.